We're going to finish up section 1.2, exploration with patterns. And we had left off on finding counterexamples. We were here, I think. Is that true? Example 3?
Yes.
Okay, I had used a different iPad, so it looks like we didn't do any of it, but we did. All right, if you'll remember, a counterexample is an example showing a conjecture's false. So basically, it's a number or a situation or something that shows that this doesn't work, that whatever we're trying to say is true, it simply isn't. So here's the first one. It says, if n is a natural number, then n plus 5 over 5 is equal to n plus 1. And we're supposed to find a counterexample that shows that that statement, that equation, if you will, is a not true equation. It doesn't work. So we're looking for numbers that fail. Not numbers that succeed. That's what you're usually looking for, numbers that work. We need a number that fails. So can somebody create, or can you think of a number, n, that will make this not work? 1. Okay, so let's give it a try. We have 1 plus 5 over 5 on the left. So 1 plus 5 is 6, so we have 6 over 5 on the left. On the right-hand side, we have 1 plus 1, which of course is 2. And these two items, I typed it wrong, or wrote it wrong. 5, hang on. 6 over 5, that's what I want. 6 over 5 does not equal to 2. Okay? So sometimes counterexamples are very easy to find. Sometimes they're not. Sometimes you're sort of looking for the trick that makes this fail. And sometimes almost every number will make things fail. It's only specific cases where it works. Part B here asks, what reason might you speculate that a student might make this conjecture? Why might some student think that n plus 5 over 5 is equal to n plus 1? What might they be doing wrong?
It could look like they're canceling out both the 5s, just marking them out, and then it's just n.
All right, so they're looking like they're taking this, and they're marking them out to give them the number 1, which would leave with n plus 1. I agree. I think that's probably what the student, if they made this error, had made the error doing, right? So why is this an error? I mean, we created an example to show that it really doesn't work. It's wrong. N equal 1 doesn't work. So what are they missing when they're canceling in this way? What have they forgotten?
That it divides the whole thing, not just the number right there.
That there's still a division of this value, the n, by 5. So if they were to cancel this or to attempt to cancel it, they would actually end up with still n over 5 and then plus 1, right? So can they cancel the 5 over 5? Well, yes, as long as they do the separation so that their n is still over the 5 because they didn't reduce the n by 5. Does that make sense? Okay. We have one more kind of topic in this section, and it's kind of a cool one. It's called figurate. I'm going to add extra syllables today. Figurate numbers. These are based on visual geometric patterns, examples that are neither arithmetic nor geometric. Such numbers can be represented by dots arranged in the shape of certain geometric figures. So our first one we're going to take a look at is called triangular numbers. So let me draw some dots that they're describing so you can see what triangular numbers look like. So it's going to look like a sequence of dots, okay? That's my first image in my sequence. And I am not very good at keeping things perfectly arranged, so you'll have to pretend like that I am. It's probably far enough. We can go that far. Okay, so the question sort of posed on this slide at the bottom says, The numerical pattern can be written as. So what we're going to do is we're going to count the dots. How many dots are in the first figure? 1. How many dots in the second figure?
3.
Third figure? 6. Fourth figure? 10. Okay, so this is the pattern. Do you agree that it is neither arithmetic nor geometric? Yes. We are going to take a look at, though, that there is a pattern. We came across one of these last time where we saw a pattern. It just wasn't the arithmetic pattern or the geometric pattern. It was sort of something else, and I said we would deal with it again today, and that's exactly what we're going to do. So I'd like for us to take this pattern 1, 3, 6, 10. I'm actually going to switch slides so I have some more room to work. And I'd like for you to notice what happens if you try to establish an arithmetic pattern. Like, what would be the plus whatevers we need for the second one? So in other words, 1 plus 2 would give me 3. So what would I have to add to 3 to get 6? 3. And what would I have to add for 6 to get 10? 4. So if I wanted to do the next term, what would I need to add? 5. Now, geometrically, that should make sense based on our picture over here, right? What does it look like is happening with this shape? It's getting bigger. How?
Like it's adding a row on the bottom every time.
Good. It's adding a row on the bottom every time, and the row that it adds on the bottom is one bigger than it was on the previous row, right? So it makes sense that we would be adding 5, and the next one we would be adding 6, and then we would be adding 7. So visually this makes sense. Okay. Back to what I wanted to show you about the numbers themselves. So we could add 5 and we could keep going, right? Watch what happens next. What if I looked at the difference between the additions that I'm making? They're all 1. So this next line of sort of looking for patterns in this process is arithmetic, isn't it? Yeah, it is. So when the second time we do this differences idea works, these are called second differences. Okay, this is second differences. If it took 3 times, we could call it third differences and so forth. So if you're not finding a pattern, you're going to be looking for some patterns and some numbers in your homework. If you're not finding an arithmetic pattern, try doing the second differences. If the second differences don't work, try doing the third differences. At some point, you're going to find a pattern because that's the pattern that your book is using as another option for you to start looking for. Okay? This one took second differences before we actually found the pattern. Knowing this, could I create the third or 3 more terms maybe in this sequence? Could I do that? Yeah. Even if I didn't recognize 2, 3, 4, 5 and then it's 6, 7, or if it were more complicated than that. Right? If it didn't just increase by 1 every time, I could eventually get this pattern to lift back up and to do other examples. All right, let's try another one. Square numbers. So I'm going to draw your picture again, just like we did in the last one. I think I did better on the triangles. Okay, after you draw the image, I want you to represent the number of dots in a sequence, like a sequence of numbers, like we did on the last slide. The numerical pattern with numbers. All right, what pattern did you find? What does your list of numbers look like? Those numbers actually should look fairly familiar to you, do they? They're squares, actually. You could take the square root of them, which is, I think, what you meant. Yeah, we could take a square root of every one of those. Perfect. They're perfect squares, right? Yeah, they actually are perfect squares, which kind of makes sense that they would form squares when I put the dots together, right? Yeah. So let's take a look, just like I did on the last one, just so that you can see that they also have a pattern, even though it's, again, not arithmetic and not geometric. So 1, 4, 9, 16. If I were to add, what would I need to add to 1 to get 4? 3. And then 4 to 9? 9 to 16? So what does it look like the pattern is? Yeah, the pattern is plus 2s. If I were to do it again, I would get common difference of plus 2, right? I'd be adding 2 every time. So even if you weren't recognizing right away, I want to just show you, because you're going to be seeing ones that are a little bit more complicated. You would do plus 2 again. You would say, okay, 7 plus 2 is 9. So 9 is the number I would need to add to 16 to get the next value. And in fact, that gives me 25, which is another square number, right? So this pattern will continue in this fashion. Second differences actually work on this one. One last example in this section. Real life actually happened kind of thing. In the fall of 2011, the newly formed Hurley College of Science and Math right here at OBU had a meeting, and on the board the value 3.1415 was written, and we were asked to find the next 2 terms in the sequence of numbers. Without talking to anyone right now, I would like for you to write down what you believe the next 2 terms in the sequence was, and explain your reasoning for why you believe that's the case. Okay, so take 30 seconds to a minute, write down the next 2 numbers you think it should be and why. Okay, a volunteer. What did you write down were the next 2 terms in the sequence? Anybody? There's not a right or wrong answer here, actually. So, some of what you wrote. Do you want to tell me? What was that?
9.
Okay. Did anybody write anything different? What did you have, Shelby? 1, 6. These are the 2 most common answers. So just to show of hands, who wrote 9, 2? Okay, a couple of you. Who wrote 1, 6? Most of you. And that's usually the way it works out in this group. So let's actually start with the 1, 6. Shelby, you said it. So why did you write down 1, 6?
Because I thought it was like a pattern with the first number starts out as 1, and then the second number following the 1 was 1 bigger than the previous number.
Yeah. So if we look at 1, 4, 1, 5, 1, 6 is a reasonable assessment for what this would be. Okay? Everybody see where that number is coming from, why you might look at that and believe that's your answer. No?
I added 1 to each time, resulting in 4.1415, 5.1415.
But there's only,
Understand.
okay, there's only 4 numbers here, 1, 4, 1, 5, and I want to know what the next 2 numbers would be. Yeah, like what would come after the 1, 5 in the ... That's what the question was asking.
Like 3, 4, 5.
No, the directions say what are the next 2 terms in the sequence of these numbers, 1, 4, 1, 5. So one option is it might be 1 6. Because if we look at the numbers, it looks like the one's alternating with one bigger each time, like Shelby had described. So where did the 9 2 come from?
Looks like pi.
Yeah. Okay, so the 9 2 might be because you looked at this number and you thought, well, it's pi. That will be the next two numbers in the expansion. Now, thinking about who is in this meeting, it said it was the Hurley College of Science and Mathematics. What do you think the predominant answer was to this particular question when it was posed to us? 9 2. I think everybody said 9 2. I don't think any of us, in fact, I know personally when I saw it, I was like, what else could it possibly be? Like, what do you mean? Like, what a dumb question. Like, that was my mindset because that's what I saw when I saw it, right? And those of you who saw 1 6 probably felt the same way. Obviously, it's 1 6. What else could it be? Because, at least in some sense, too, especially because of the values we've been looking at in this particular section, that's the way the patterns have been going. So thinking about this, what does this tell you about inductive reasoning? Because that's what we just did. We all did inductive reasoning. We looked at a pattern and we speculated about what the pattern was doing and what would come next. What does it tell you about inductive reasoning? It can be faulty, right? It can lead you to conclusions that are different from someone else, and you both have very legitimate and good reasons for thinking that it should be the way that you saw it, right? Inductive reasoning doesn't always lead us to the same conclusion as someone else, or to the right conclusion, or however you want to phrase that. So keep that in mind. Inductive reasoning doesn't always sort of work.